Now this is the second part of Euclid Book 2 proposition number 14, and like I say, the reason why I had that drawing done first is because I wanted you to see how we actually constructed this figure right here. If you'll remember from Euclid Book 1, propositions 42 and 45, we bisected this line here, and we duplicated this triangle. The area inside of this triangle is equal to the area inside of this parallelogram. And the area inside of this triangle is equal to the area inside of this parallelogram. So now, what we're going to do is we're going to draw this parallelogram. We're going to duplicate it over here. And now that parallelogram is going to become B, C, D, E. Okay? So the area inside of this parallelogram is now equal to the entire area of this figure A. Alright? You saw how we did this in the previous video, so I won't have to cover that again. Alright. Now, Euclid says, first of all, he wants you to draw a line from point B to point E, and this line here, of course, is part of this parallelogram that we just drew. And he wants you to extend that line all the way out to F. Okay? And then what he wants you to do is he wants you to bisect line BF. Well, here's line BF. You're going to bisect it at point G. And then you're going to use your compass. The center part of the circle is going to be G, the outermost edge is going to be B, and you're going to draw this little arc right across here. And it's going to start at B, it's going to go all the way through to H, and it's going to go all the way down to F. So you're going to have an arc B, H, F. And when you do, you're going to draw a line from point E, because remember this is ED, you're going to extend that line ED, you're going to extend all the way out to H. Okay? And then you're going to draw another line, and it's going to come from point H down to point G. All of this is given to you by Euclid. Then he wants you to start the proof. Well, alright. We're going to start the proof. Let's see. First of all, the rectangle formed by line BE, well, here's line BE, and EF, which is this line right here. If you were to draw EF up through here, okay, you'd have another rectangle. Okay, so and the rectangle would have a side of BE and the other side of EF. Of course, you have two other sides being equal to, you know, you'd have one here equal to this and one here equal to that, so that you'd have a perfect rectangle. Okay, so rectangle BEEF plus the square on EG. Now, we've been talking about this for quite some time. This is a square on EG. Alright? If you add the area inside a rectangle BEEF and the area inside a square EG, it will become the area of square GF. Well, here is G, and here's F, and the square GF would be down here someplace, if you were to draw it out. Now, line GF is also equal to line GH. Well, here's line GH, here's line GF, here's line GH. And why is this so? Because all radii of a circle are equal. Okay? And remember, we drew a line from, with centermost G, the outermost point B, and GB is also equal to GF, because these two are radii, so that makes GH also a radii of this BHF, and therefore it's a radii of the circle, and so GF equals GH. Whew. I think you got the point. Alright, so that means that rectangle BE plus EF, well, okay, rectangle BEEF, well, we were talking about rectangle BEEF, and we'd make a rectangle up here, okay? Rectangle BEEF plus the square of GE, which is the area of the square of GE, equals the area of square GH. Like that. Now, the thing is that the area inside of square HE, well, here's HE, and we can make a square out of it. and the area inside of square EG, well, here's EG, we can make a square out of it. Those two areas combined would be the area contained in square GH if we were to draw it out. So that also means that the rectangle BEEF, which this is BE, this would be EF, and we'd make a rectangle out of here. The area inside of that rectangle plus the area of GE, which is this right here, would equal the area of HE, which this is HE right here, and the area of GE right here. Okay? These are two squares. And I bet you noticed by now that this is a right angle triangle. I know it's kind of small, but it's a right angle triangle. Alright, now we're going to subtract the square of GE, which is right here, from both sides of this wonderful equation that we just talked about a minute ago. So the area inside of rectangle BE times EF, so here we go again, here's rectangle BE, EF, we'd have a rectangle right up here, would equal the area of HE. Okay, here's square HE across here. Now, the thing is that rectangle BE and EF, this rectangle up here, would be equal in size, equal in area, to rectangle BCDE. This rectangle right here. So you'd have two rectangles on top of each other, sort of like bunk beds. One up here, one down here, and the area inside of both of them would be exactly the same. Alright, and the reason why we know this is because ED right here would be equal to EF. So the area inside of these two rectangles would be the same. So that means that the rectangle BE and ED, which this is BE and this is ED, the area inside of here, is equal in area to the square of HE, which is right across here. Now we already established that the area inside of here was the same as figure A. And that's figure A right here. So therefore, the area inside of figure A, this area right here, because this rectangle is the same area as figure A, then figure A, the area inside of it, would equal the area inside a square HE. And that's what Euclid wanted you to prove. We have thus concluded Euclid Book 2. We will be moving on to Euclid Book 3. Stay tuned, you won't want to miss that.